How can we estimate frequency response functions from measured data? That is the question that we are going to discuss in this first presentation of frequency response function estimation. So we are going to talk a little about frequency response functions and how it is connected to the measured data. We are going to start a discussion about measurement errors, and in the later presentation we will discuss a method to estimate the frequency response function in order to reduce the influence of the measurement errors. So first of all, the task we have. Well, what we want is a reliable estimate of the frequency response function between an exciting force and a responding acceleration. So the defining relationship for the accelerance function in this case, where we want the responding acceleration over the exciting force, is simply the ratio between the two signals' frequency spectra. Both these vectors, both these signals are represented as finite length vectors with sampled values, and the sampling rate is typically 48 kilohertz. So that we have, so the point is that we have vectors with finite sampled values of the acceleration and the force. So how do we proceed then to process these signals in order to get as good estimate of the frequency response function as possible? Well, first of all, we need to design an estimation procedure that sort of considers these errors in the best possible way. And one type of error that needs consideration is random errors. That is contributions from signal components that happen, well, not regularly, but occasionally. Someone might, for instance, happen to slam the door in a measurement, and this door slamming might give a contribution, an unwanted contribution to the signal that needs to be taken care of. It might also be contributions to the response, acceleration in this case, that are not caused by the excitation force Fn, but from other sources that contribute. So how do we reduce the influence of this kind of response contributions? Then, of course, we have errors that is introduced by the signal processing itself. When we do something with the signal, then we change the signal in some way. And that, of course, will have some influence of the estimated frequency response function. And how do we minimize, how do we reduce this influence from the signal process? We will start with one type of important error that is called leakage error. And that is an error that is caused by the fast Fourier transform. That is, it's one example of an error introduced by the signal processing. To start with, suppose we have a measured signal. So we start the measurement at time 0, and we finish it at time Tm. So Tm is the time record length. And the FFT, the fast Fourier transform, assumes that the measured signal is Tm periodic. That is, that this measured signal is repeated and has been repeated periodically with period Tm. So in this case, so we have this situation. And of course, since we assume that the measured signal is Tm periodic, which it's maybe, but most likely is not, then we introduce an error. We introduce a mismatch error in the section here when the repeated signal is joined with a measured signal. So if we zoom in here, then we can see here that in the connection, in the coupling point with the measured signal and the continued signal, we have a synthetic jump. This is not here. This is something that we have introduced by the FFT assumption, with the periodicity assumption. And this kind of sudden jumps in a signal will create a heaviside-like discontinuity. This green line here is a heaviside-like discontinuity. And that will imply a wide frequency band signal energy. So this jump here will add a wide frequency range of energy to the Fourier transform, to the FFT of the signal. It can be shown then that this heaviside-like function will introduce error spectrum, where the error is the frequency components is proportional to 1 over the frequency, so it will fall down like this. So how do we do then to reduce this error? Well, of course, we have to reduce the size of this jump. So if we can make this discontinuity as small as possible, then we reduce this contribution from this kind of error. And what we use is something that is called a weighting window. And in this case, where we have a sort of random-like signal, then we apply something that is called a weighting window, a weighting window that's called the Hanning window. And in principle, this is a sine square or cosine square signal, and it's 1 in the middle point here, and it's 0 in the end points. So if you apply this window, multiply this window with the original signal, then we will have no discontinuity at all when we periodically extend this signal. So this is the weighted signal, and this is the continued signal.